Okay, here we have topic 10, current of electricity. So these are the circuit symbols that you need to look at. We'll check these in class, but you should be able to find them anywhere. Just be aware that the resistor is the box-shaped resistor. Okay, so if we just draw a little box, it looks like that. Instead of the zigzag line that is commonly used in other parts of the world. Now, defining current, okay, essentially we define current the same way we define charge. Charge is supposed to be defined first with the formula we're going to look at, but it sort of can be used both ways. But be aware that this is actually the definition for charge, as mentioned down here. So definition, okay, so putting in the definition here for current, we could say it's the rate of flow of electric charge past a point per unit time. Okay, it's a little bit big, just reduce that. So there's one definition that we can use there. Symbol is I, formula, hopefully you can remember this, but essentially the actual definition formula is Q equals IT. But if we want it as I, well then it's going to be I equals Q over T. What's the unit? Okay, remember it's the ampere. Okay. What do we use to measure the current? Okay, well hopefully you'll remember that it's the ammeter. So ammeter. Okay. Where should it be placed in the circuit? Well, it should be in series. Okay. So what does that mean? Well, let's say we had a resistor like this and another resistor like that. And let's just connect them up with some wires. Now I want to measure the current at this point here in the center. Okay, so to do that, I actually have to physically break this circuit. What I'm going to do is just shorten that wire. Just imagine that I've deleted a bit of that circuit and then left a hole there. So I've actually broken the circuit and I then put in my ammeter. So that's a nice round circle and there's my ammeter. Okay. Because I've put it into the circuit, so I actually put it in the way, it must have 0 ohm resistance. Okay, no resistance, because if it did have resistance, then it would actually affect what's happening in the circuit. How does current behave in series? Okay, just a few things to remember. We'll do this more in class, but generally, current is the same everywhere in a series circuit. Okay, so remember series is where everything is just in one line, okay, or one loop, essentially. It's going to be the same everywhere in a series circuit. That's all you have to remember. It's sort of like the flow of a river. No matter how many waterfalls and so on it goes over, there's still going to be the same amount of water flowing past a point a second. Or you can think about traffic. If there is a region on the motorway where there is a lesser current, well then the cars would actually be piling on top of each other, and that doesn't really happen. Okay, so the current is the same everywhere in a series circuit. So if we just did draw a series circuit, I'll just sketch one. So resistor, and let's put in a cell, and maybe another resistor. So if we measure the current there to be 1 amp, well, it's going to be 1 amp there, 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 everywhere, okay? So the flow of that current is the same everywhere. Okay, it's only different for a parallel circuit, which we'll get into soon. So current and parallel, how does current behave in parallel? Well, effectively we no longer have just one loop, okay? So we have two loops for parallel, so two different paths that the current could flow. What I'll do is I'm going to draw it this way, it's easier to see the two loops. So there's the cell, so there's one loop, and let's draw another loop. Okay, so what's going to happen here, current's going to flow out of the cell this way, okay, and then it's going to head this way, and it's going to head that way, and then come back in this way. So, current flowing through here, the current is essentially driven by the battery, okay, or the cell here, so that remember is the EMF, which we'll get into soon, is actually driving it, and as it gets to here, it's going to split at the junction. Okay, so how does the current behave in parallel? Well, it splits up depending on the ratio of the resistors. So let's write that in. What is a junction? Okay, and you've got to be aware that where does it actually split? Well, it actually splits at a junction. Okay, depending on the ratio of the resistors. What is a junction? Well, let's just put one out. Okay, so where wires have different paths at a point, then that is a junction. This example we'll look at in class. Potential difference, definition, and dictionary or the video. So in this case, it could be the definition here. So what is the actual definition? Let's write it out. So we can write the definition like this. Let's just do shorthand potential difference. Potential difference between 2 points is the work done per coulomb of charge transferring a small positive charge from one point to another. Okay, it's also it is a scalar. Okay, so that's one way of doing it. The simplest option is always going to be just doing the actual formula itself. So you can write it all out on words. So potential difference. Okay, not just freehand here. I'm using a mouse, so it's a bit harder. Potential difference equals work done work done over the charge. Okay, so formula. Well, what's the symbol for potential difference? It's here, V. So V equals work done, which is capital W, divided by charge, which is Q. Okay, what's the unit? Well, it's the volt. Okay, V again. So if you can imagine what this is, as charge is flowing from here to here, okay, and let's say on the way it goes through a light bulb, then there's going to be a change in energy from the light bulb. Okay, it's going to go from electrical energy to light and heat. Okay, so electrical energy to light and heat. So there's a change in energy there. And so let's say you measure 5 joules per 1 coulomb here. Okay, and then you may actually get 3 joules per coulomb here, per 1 coulomb. So what is the actual potential difference? It will be equal to 2 volts, or 2 joules per coulomb. So remember, the potential difference should not be described as flowing, it is a reference measurement. So like I just did before, when you attach a voltmeter, you're looking at the reference from one point to another, okay, and the difference between those 2 points in terms of how much energy per coulomb there is the potential difference. So it's essentially how much work is done in moving a charge from one point to another. So a couple of examples here. 230-volt motor is connected to a main supply. Find the work done when 8 coulombs of charge flows through the motor when lifting a brick height h. Okay, what happened with that T? So I'll let you guys work this one out. We'll do this in class, but it's a question for you to do. Okay, EMF. Well, EMF stands for electromotive force. Okay, it's not really a force, so let's just call it EMF. Just don't worry about it being a force or anything. Definition, well, essentially look in your dictionary, but it's similar to potential difference. Instead of having a lots of energy around the circuit, there needs to be a point where energy goes into the circuit. In other words, from some other type of energy like chemical into electrical energy, and EMF is the energy going in. So it has the same symbol, same unit, same formula as potential difference. Okay, the difference being is that it's energy in. Okay, so EMF is energy in, potential difference is energy out. Now, so resistance here. Resistance we described as impediment to the flow of current, or as a means to convert electrical energy into other forms of energy. So think of a light bulb. It's a resistor. It is there to convert energy from electrical into heat and light. A plain old resistor, well, that just creates heat energy. Okay. Final definition, well, essentially it's the ratio of two things. So if I just draw the formula, when we define resistance, R equals V over I. So it's the ratio of potential difference to current through it. So remember, this is both the energy provided, so the amount of kinetic energy you have, and this is essentially the speed you're going. So you can imagine running in mud. So here's some person, okay, and he's running along, okay, not this image here. He's running along. If this person was buried down in deep mud, okay, he might still have a lot of energy, okay, might be able to provide the same amount of power or something like that, but essentially because of the mud resistance, he will be going a lot slower. Okay, so this is a ratio here to show how the resistance affects the current. So if you put in, let's say, 10 joules per coulomb of energy, or you use that much energy, then your current will vary depending on the resistance. The unit is the ohm, okay, So really, remember, one thing is essentially that resistance changes the current, okay, depending on what voltage is set. So this is an experiment we're going to do in class. Essentially we're going to look at IV characteristics of the currents for a resistor compared to the potential difference across it, and then we're going to compare it to a lamp and graph them.
proper sketches. Okay, so let's just do some graphs now. If we look at the IV here of two things, so we're looking at a lamp and resistor. So the resistor is essentially going to be like that. Okay, just a straight line.
So this one here is the resistor. Okay. Should we label the axes? We might as well. So this will be I and A. Okay. And then this one here is going to be V and V. Okay. And pretty similarly here, labeling this one, this is going to be the lamp. Now, what happens here is this one's actually going to be curved. Okay. So if we've got a current up there, voltage down there, it's actually going to curve this way here. Okay. Which probably doesn't actually go to a flat line. It will just curve off like that. And going the other way is opposite like that. So remember, this is I and V. Okay, so what happens here, you can see as you increase the potential difference across it, okay, or the energy lost, you actually start decreasing the amount of increase in current. So in other words, it's actually getting harder to get through. Okay, so you're pushing harder or you've got more energy available, but you're not really flowing faster. Okay, so what's happening in the lamp is essentially the resistance is increasing. With a resistor, the resistance is constant. Now the difference between the two is the temperature. So essentially Ohm's law is saying that if you can keep temperature constant, then the current is proportional to the potential difference. Oh, well actually both of them actually do increase the temperature. This one is actually going to increase it by, let's say, 50 degrees. But this one here, a lamp actually burns at about 2000 degrees. So there's a big difference in temperature. Now note that resistance is not found by finding the gradient of a graph at a particular point. You just divide the potential difference by the current at the point you're referring to. Okay, so in other words, if I want to find the resistance there, do not do a tangent or anything. Oh, sorry, do not do a gradient point to that line, just or a tangent. Just do whatever the value of V is divided by the value of I, and that will be your resistance. We just talked about that. A couple of things that affect resistance.
Okay, one is a type of material. Okay, the property here is actually called resistivity.
Okay. So when you change the type of material, you're going to change a particular, it's going to change the actual resistance of it, and we call it the resistivity. Change the length of a material, it's going to change the resistance, and also the cross-sectional area of the material. So resistance is proportional to length. So if you actually increase the length, you increase the resistance. Okay, so directly proportional. It is inversely proportional to area, okay, the cross-sectional area. Increase the area, you're essentially making the pipe bigger, easier to get through, so resistance goes down. So area goes up, resistance goes down. The material itself has a constant proportionality called resistivity. It only varies when you change the material, i.e. copper to iron. Okay, so the actual material itself has a particular constant and it's called resistivity. Symbol and unit. Okay, rho is the symbol. Okay, and I'll let you find the unit. Okay, you can find that from the formula. So the formula for physical resistance. Okay, so R, this is resistance depending on the material and material's properties, is rho A over R. Is that right? Don't know, let's have a check. So if we increase resistance, sorry, if we increase area, do we increase resistance? No, that's not right, is it? So let's try that again. So looking at what we did before, here we go. So resistance is proportional to length. Okay, so increased length, you increase resistance. Resistance is inversely proportional to area. So in other words, if I write this out as a proportional equation, it will be length, that's an L by the way, it will be an L divided by A. Okay, so resistance proportional to length over area. So putting that into the formula, making it equals by putting in a constant, in this case it's resistivity, and we have length divided by area. Okay, and you can work out that equation yourself. Just remember, radius is not area, so there's a difference there. A thermistor is a resistor whose
resistance varies greatly with temperature. Okay? So let's say we have resistance here and we have temperature. With a thermistor, as you increase temperature, so going this way, you're actually going to decrease resistance. This is actually opposite to a light bulb. Okay. So increase temperature, decrease resistance. So in this case, resistance is proportional to 1 over the temperature. Okay.
power. Same definition of what we've
seen before. Set the change in energy involved with its energy. So what is the power equation? The power definition is work over time. We know that the potential difference can measure energy transfer per unit charge, and the current is a measure of the rate of flow of charge. So what's the definition of work according to potential difference? Was V equals W over Q, so this is W equals VQ. And we want to know the amount of charge at any one time, so we have Q equals IT. And you can probably see how that and those two equations will relate to that. So what we're going to do is combine them all, and then you get that equation there, P equals VI. Using V equals IR, we can now substitute into P equals VI to get two other equations. I'll do one of them for you. So if you have P equals VI, let's say we put in V equals IR into this equation. So instead of having V, let's put in IR as the same thing as V. So we're going to get rid of that V and we'll replace it with IR. And we're going to multiply that
by another I, and so that equals I squared R. Okay, so power is equal to I squared R. A couple of examples there. And essentially that equation there, P equals I squared R, is what we call the heating formula. In other words, heating effect formula. So it actually tells you for a constant resistance what current can do to the amount of energy released. As you send stuff down power lines do actually have a resistance, so you will actually get some sort of power release. In other words, amount of energy converted into heat. Okay, so it's wasted energy. Higher the current, the higher the power, amount of energy released. So really when you want to send power down, electricity down power lines, you want to have a low current. Okay, you want to have a low current to reduce the power output. It's a big effect because of that square. And now we'll get into classwork.